Voyager 1 is already farther from Earth than anything humans have ever built. But the real question is not where it is now. It is where it will be when every nation alive today is history, when the night sky itself has changed, and when its signal has been dead for ages. In 1 million years, will it have reached another star, left the solar system for good, or barely moved on the scale of the Milky Way? The answer is much stranger than most people think, because in space, a distance that sounds impossible can still be almost nothing. But before we continue, please subscribe to the channel to give your support. Let's continue. If you measure from Earth, Voyager 1 is already unbelievably far away. It is farther than anything humans have ever built. But Earth is moving. Earth goes around the Sun. So even that answer is not fixed. If you measure from the Sun, you get a cleaner answer. Voyager 1 is moving away from the Sun at about 17 kilometers per second. That is about 61,000 kilometers per hour, or about 38,000 miles per hour. That sounds extreme, and on human scales it is, but on galactic scales, it is not. That is the first thing that changes the whole question. Voyager is fast by human standards. It is not fast by the standards of the galaxy. So when people hear 1 million years, they often think Voyager must end up insanely far away, maybe in some distant part of the Milky Way. That is not how this works. 1 million years is a huge amount of time for us. It is far longer than recorded history. It is longer than countries, languages, and civilizations last. But for the galaxy, 1 million years is still a short stretch of time. Stars take hundreds of millions of years to go around the Milky Way, so Voyager can travel a huge distance and still remain in a very small part of the galaxy. That is why this question is harder than it looks. You are not just asking for a distance, you are asking for a frame of reference, and those are not the same thing. Voyager 1 is also no longer in the kind of mission people usually picture. It is not flying toward a target the way a mission flies to Mars. It is not going to enter orbit around some destination. It is not heading toward a planned arrival point. It is moving on a path set long ago, and now that path is being carried forward by speed, direction, and gravity. So the right way to think about it is not destination first. It is motion first. Its future position depends on how fast it is moving now, which direction it is moving, how the Sun is moving, how nearby stars are moving, and how gravity changes the path over very long times. Even weak effects matter when you stretch the clock out to 1 million years. And there is another layer to this. The Sun itself is not standing still. The solar system is moving through the Milky Way. Nearby stars are moving too. So when you ask where Voyager will be, you are asking about the position of one moving object relative to other moving objects inside a moving galaxy. That means there is no single simple cosmic map with everything frozen in place. There is no fixed background where you can just draw a straight line and be done. Over short times, that kind of simplification works. Over 1 million years, it starts to fail. This also changes how you think about distance. A spacecraft can be unimaginably far from Earth and still not be very far in galactic terms. Both statements can be true at the same time. That is one of the hardest parts of space to really feel. Voyager 1 is already leaving the Sun's immediate neighbourhood. The planets are far behind it. The mission phase people know best, the part with Jupiter and Saturn, is ancient history now. That version of Voyager is over. What remains is a spacecraft moving outward into deep space, farther every year, with less and less connection to the world that launched it. But even that needs care. Leaving the planetary region is not the same thing as leaving the Sun's full sphere of influence. Space does not have neat walls. The Sun's gravity gets weaker with distance, but it does not just stop. So even when we say Voyager is leaving the solar system, the exact meaning depends on the definition. And that brings you back to the main point. The word where sounds precise. In deep space, it is not precise until you define the frame. Now take the timescale seriously. In 1 million years, Voyager 1 will not be an active spacecraft. It will not be sending back data. It will not be taking pictures. It will not be doing science in the normal sense. Long before then, its power will be gone. Its systems will be dead. It will be silent. So this question is not really about the future of a working mission. It is about the future of an object. A human-made object built in the 20th century, still moving through space long after its mission has ended. That changes the tone of the whole story. Voyager 1 in 1 million years is not a probe doing exploration. It is more like a leftover trace of a civilization. A physical remnant of the moment humans first pushed machines beyond the planets. That is why this topic gets so big so quickly. You start with a location question, then it turns into a motion question, then into a scale question, then into a time question. So before we even try to answer where Voyager 1 will be, we have to settle something more basic. How much ground does 17 kilometers per second actually cover when you give it 1 million years? And why does that still not mean Voyager is getting very far by interstellar standards? 17 kilometers per second sounds like the end of the argument, but it is really the start of the confusion. Because if you compare that speed to life on Earth, Voyager 1 sounds almost absurdly fast. If it could move through air like that, it could cross entire countries in minutes. It is moving at about 61,000 kilometers per hour, or around 38,000 miles per hour. That is way beyond normal human experience. No car, no plane, no bullet train gets close to making that feel ordinary. But space changes the meaning of speed. That is the part people miss. A speed can be extreme on Earth and still be limited in deep space. That is because the distances are so large that your normal instincts stop working. In everyday life, if something moves fast, it gets somewhere soon. In astronomy, something can move very fast and still take tens of thousands or millions of years to get anywhere important. So is Voyager 1 fast? Yes, very fast by human standards, not especially fast by interstellar standards. And that difference is the whole story. The nearest star system, Alpha Centauri, is about 4.37 light-years away. Voyager 1 is not heading there, but that distance helps show the scale. At its present speed, Voyager would not get to a nearby star on any timescale that feels human. Not in a lifetime. Not in recorded history. Not in the rise and fall of civilizations. In space, the real enemy is not lack of speed, it is the size of the map. That is why you have to compare speed to astronomical distance, not Earth distance. On Earth, 17 kilometers per second is almost impossible to relate to. In space, it becomes something you can measure cleanly, and once you do that, the result is both impressive and strangely limited. The math itself is simple. Distance is speed multiplied by time. That part does not change. What changes is the scale of the answer. At roughly 17 kilometers every second, Voyager 1 covers about 540 million kilometers in 1 year. In imperial terms, that is about 336 million miles per year. That is a huge number. Even for a single year, it sounds almost unreal. Now stretch that over 1 million years. If Voyager 1 keeps moving on roughly its current path away from the Sun, it would cover about 540 trillion kilometers. In imperial terms, about 336 trillion miles. Those are the central numbers, and those numbers are real enough to matter. This is not a tiny drift. This is not a symbolic change. Voyager really will go incredibly far. But then the next problem hits. Even that is still not truly far by interstellar standards. This is where the word light-year becomes necessary. A light-year is not a measure of time here. It is a measure of distance. It is how far light travels in 1 year. And light moves at about 300,000 kilometers per second, or about 186,000 miles per second. So when you convert Voyager's 1 million year travel distance into light years, you get roughly 57 light years. That sounds huge, and it is. 57 light years is far beyond the nearest stars. It takes Voyager out past our immediate local neighborhood. It means that over deep time, this spacecraft really does move into a different part of nearby interstellar space. That matters. But now compare 57 light-years to the Milky Way. The galaxy is about 100,000 light-years across. Suddenly, Voyager's million-year journey looks small again. Not small in human terms, small in galactic terms. That means after 1 million years, Voyager 1 will still be deep inside the Milky Way, still inside the same galaxy, still nowhere close to crossing it, still inside a very local part of the bigger structure. So this speed does two things at once. It takes Voyager unimaginably far from us, and not very far at all on the scale of the galaxy. Both are true. And if that feels contradictory, that is because space keeps forcing human intuition to fail. This is why comparisons can help, but they can also mislead. You can say Voyager moves faster than a rifle bullet over long duration. You can compare it to jets, rockets, or orbital speeds. You can say it is fast enough to go around Earth in a short time if it were near the surface. All of that is true. But those comparisons can trap you into thinking the spacecraft must be racing across space in some overwhelming way. It is not. Not in the sense people usually imagine. The better comparison is not about violence or machines. It is about mismatch of scale. Voyager is covering real distance, constantly, every second, every year. But the space between stars is so large that even this pace does not produce quick arrival. It produces long drift. That is a very different feeling. And there is another point that matters. When you say Voyager travels at 17 kilometers per second, you have to ask, relative to what? That speed is usually given relative to the Sun. That is useful, but it is not the only possible frame. Relative to Earth, the number changes because Earth is moving. Relative to the center of the galaxy, the picture changes much more because the Sun itself is moving around the Milky Way much faster than Voyager is moving away from the Sun. So even the speed number that sounds so solid is already tied to a frame of reference. That does not make it wrong, it just means it is not the whole story. And once you push the timeline to 1 million years, frame of reference stops being a technical detail and becomes a major part of the answer. This is also why you cannot treat Voyager's future like a straight-line highway trip. If all you want is a rough first estimate, speed times time works very well. That is how you get the 540 trillion kilometers, the 336 trillion miles, the roughly 57 light years. Those are good first-order numbers. They are the right place to begin. But they are not the final word. Over 1 million years, small effects matter. The Sun's gravity still shapes the path for a long time. Passing stars can alter trajectories slightly. The local galactic environment is moving. The Sun is moving. Nearby stars are moving. So the real future position of Voyager 1 is not just a simple ruler measurement from one frozen point to another. That is the deeper point in this section. Speed matters a lot. Without speed, there is no journey. But speed alone does not answer where. It answers only how much motion Voyager carries right now, in one chosen frame, before the rest of the universe starts changing the context. And that should raise the pressure immediately, because if 17 kilometers per second can take Voyager 1 about 57 light years in 1 million years, then the next question becomes unavoidable. What has it actually escaped already, and has it truly left the solar system? Or are we still using that phrase too loosely? Voyager 1 feels like it should be gone from the solar system already, but that depends on what you mean by the solar system. That is the problem. People hear that Voyager is in interstellar space and they think it has fully left the Sun behind. That is true in one sense and not fully true in another. Start with what is clear. Voyager 1 left the planets behind a very long time ago. Jupiter and Saturn were once the big targets. They were the reason this mission became legendary in the first place. Back then, Voyager 1 was a planetary probe. It was flying past giant worlds, taking images, measuring atmospheres, looking at moons, and changing what humans knew about the outer solar system. That version of the mission is over by a huge margin. Those encounters are not recent milestones anymore. They are ancient history in the life of the spacecraft. Jupiter and Saturn are now far behind Voyager 1, not just physically, but as part of the story. The mission changed from exploration of planets to something much stranger, long-term drift into the space between stars. That change matters, because it shows that leaving the solar system is not one single event. Voyager did not pass one line and suddenly switch from one kind of universe to another. It passed through stages. First, the inner solar system was behind it. Then the giant planets were behind it. Then the Sun's outer environment became the next boundary. And that brings you to the first really major border, the heliosphere. The Sun is not just a bright object sitting in space. It constantly sends out the solar wind, a stream of charged particles flowing outward in all directions. That flow creates a kind of bubble around the Sun. That bubble is called the heliosphere. Inside it, the solar wind and the Sun's magnetic influence shape the environment in a major way. Outside it, the interstellar medium becomes more important. Voyager 1 crossed the heliopause, which is the boundary where the outward push of the solar wind stops dominating and the interstellar medium takes over. That was a huge moment, because it meant Voyager 1 moved beyond the sun's protective bubble in a real physical sense. This was not just symbolic, it was a measurable transition in the local space environment. But even that does not mean Voyager suddenly entered a completely different universe. The word boundary can mislead people. It sounds sharp and clean, like stepping through a door. Space is not like that. The heliopause is real, but it is not a brick wall. It is a transition zone in a complex plasma environment. Conditions change, particle populations change, magnetic behavior changes, but the universe does not split cleanly into one thing on one side and something totally unrelated on the other. So yes, Voyager 1 crossed into interstellar space in a meaningful scientific sense. That statement is correct. But then another question immediately appears. If it crossed into interstellar space, does that mean it has left the solar system completely? That is where the answer gets less comfortable. If by solar system you mean the region of the planets, the place where the sun rules through the main planetary architecture, then Voyager is absolutely beyond that. No serious argument there. The worlds people normally think of when they hear solar system are far behind it. In that simple sense, Voyager has left. But astronomy has a wider version of the solar system too. That version includes the Oort Cloud, the huge and distant population of icy bodies thought to surround the sun far beyond the known planets. The Oort Cloud is still partly theoretical in structure, but it is the standard idea for the far outer reservoir of comets and icy debris linked to the sun's long-range gravitational influence. And if you include that outer domain, then Voyager 1 may still be inside the sun's broader neighbourhood for a very long time. This is where a lot of people realise space has fewer clean endings than they expected. You can leave the planets and still not be fully beyond the sun's deepest reach. You can cross the heliopause and still not be fully outside the sun's broader gravitational domain. Those are different layers of leaving. That is because gravity does not switch off. It weakens slowly, very slowly. The sun's pull drops with distance, but it never goes from on to off in one step. There is no final hard wall where you can point and say, beyond this line, the sun has nothing more to do with Voyager. Real space is messier than that. So even 1 million years from now, depending on the definition you use, Voyager 1 could still be described as being in the far extended outskirts of the sun's sphere of influence, or at least moving through the outer region shaped by the path it inherited from the solar system. That does not mean the sun strongly controls it forever. It means the transition from solar system object to fully independent galactic drifter is gradual, not sudden. And that matters for the bigger question of where Voyager will be, because if you use one definition, it has already left. If you use another, it is still leaving. There is another phrase that can also confuse people. Interstellar space. That phrase sounds like pure emptiness. It sounds like Voyager is now moving through nothing at all, but that is not true. Interstellar space is incredibly thin, yes. By human standards, it is basically vacuum. There is almost nothing there compared with even the emptiest environment on Earth. But almost nothing is not the same as nothing. Interstellar space contains atoms, ions, magnetic fields, dust grains, high-energy particles, and large-scale structures shaped by stars and shock fronts. It is a medium, an extremely sparse one, but still a medium. That is important because Voyager is not moving through perfect emptiness. It is moving through a real environment. That environment is thin enough that it will not stop the spacecraft quickly. Voyager will not suddenly slow down like a car moving through air. It will not burn up. It will not hit some hidden wall. But over huge spans of time, even a very thin medium matters. Radiation matters. Dust impacts matter. The interstellar environment is weak in the moment and powerful across deep time. So when people say Voyager has entered interstellar space, the right picture is not total emptiness. The right picture is a region where the sun is no longer the main force shaping the local plasma environment, and where the background of the galaxy begins to matter more. That is a huge transition. But it is not the end of the story. It is the start of a new one. And this is what makes Voyager 1 so hard to place in simple language. It has clearly escaped the age of planets. It has crossed a major physical boundary at the heliopause. It is travelling through interstellar space. And yet the larger question of whether it has fully left the solar system depends on how large a solar system you are willing to define. That sounds technical, but it changes the emotional scale of the mission. Voyager 1 is farther than any human-made object has ever gone, and even now space still refuses to give us a simple final line to point at, which leads to the next tension point. If Voyager has already gone this far, and if leaving still has layers, then how much distance will it actually cover in 1 million years? In hard numbers, not just in dramatic language. How far is 1 million years of motion, really? This is the point where the question stops sounding vague and starts turning into a number. Because once you know Voyager 1 is moving away from the Sun at about 17 kilometers per second, you can finally do the rough calculation people actually want. If you keep that speed and stretch it across 1 million years, Voyager 1 would travel about 540 trillion kilometers. In meters, that is about 5.4 times 10 to the 14th. In imperial terms, that is about 336 trillion miles. That is the core number. That is the distance Voyager can cover in deep time if its motion stays close to its current path, away from the Sun. And yes, that is an insane number by normal standards. 540 trillion kilometers is so far beyond everyday experience that the number almost stops meaning anything. That is why space stories always hit this wall. You get the number, but the number is too big to feel. So the next step is to convert it into the unit astronomy uses when kilometers stop being enough. Light years. That 540 trillion kilometer figure comes out to about 57 light years. That is the most useful way to say it, because stars are usually discussed in light years, not kilometers or miles. The moment you say 57 light years, the picture gets clearer. Voyager 1 would move well beyond the very nearest stars, well beyond the immediate space around the Sun, but it would still remain in the local part of the Milky Way. That is the balance you have to hold in your head. 57 light years is a huge distance. It is not a small drift. It is not just barely leaving home. It is real interstellar travel. But it is still local in galactic terms. That is the part people underestimate. Now there is a catch. About 57 light years is a rough estimate, not a perfect forecast. It is the right first number, but it is not the final one. Why not? Because real motion in space is not just one straight arrow drawn on a frozen map. The Sun is moving. Voyager is moving relative to the Sun. Nearby stars are moving too. Gravity keeps acting over long periods. Even weak effects can matter when you give them 1 million years to build up. So Voyager will not just sit on a static star chart and move in a perfectly clean straight line away from a perfectly fixed Sun. That means the 57 light-year figure is best understood as a first-order answer. It tells you the scale. It tells you the magnitude. It tells you that Voyager 1 will get very far from the Sun. But it does not mean there is one exact point on today's map where you can place it and say, that is exactly where it will be. Still, even as an estimate, 57 light-years is enough to make the situation very clear. It gives you the right sense of distance, and it lets you compare Voyager's future position with things people already know. Start with Alpha Centauri. That is the nearest star system to the Sun, at about 4.37 light-years away. Voyager's 1 million year travel distance is more than 10 times that. So if you only compare it to our nearest stellar neighbour, Voyager's future journey sounds enormous. It is not just edging toward interstellar space, it is cutting deep into it. But then compare 57 light-years to the Milky Way, and the scale flips again. The galaxy is about 100,000 light-years across. So 57 light-years is only about 0.057% of that width. That is tiny. Not metaphorically tiny, numerically tiny. Voyager could travel for 1 million years and still cross only a minute fraction of the galaxy. This is why the answer feels strange every time you say it out loud. In 1 million years, Voyager 1 will go farther than anything humans have ever made by an absurd margin. Farther than the nearest stars, farther than the distances people usually even talk about, and still not get anywhere close to crossing the Milky Way in any serious sense. That is not a contradiction. That is just how large the galaxy is. And the human brain usually needs one more step before it really lands. Numbers like 336 trillion miles sound huge, but they still do not always connect. So it helps to compare Voyager not just to stars, but to light itself. Light moves at about 300,000 kilometers per second, or about 186,000 miles per second. Voyager moves at about 17 kilometers per second, or about 38,000 miles per hour. That gap is everything. Light would cross Voyager's 1 million year travel distance in just 57 years. Voyager needs 1 million years to do what light can do in a few decades. That comparison cuts through the fog fast. Voyager is not slow in any human sense, but compared with the speed limit of the universe, it is crawling. And that is why even 1 million years of travel produces a result that is both enormous and limited at the same time. This also helps explain why interstellar travel is so hard. It is not enough to say a spacecraft is moving fast. You have to ask, fast compared to what? Compared to a plane, Voyager is absurdly fast. Compared to Earth orbit, still very fast. Compared to the distances between stars, it is modest. Compared to light, it is extremely slow. And once that clicks, the whole topic becomes more grounded. Voyager 1 will not vanish into some unreachable corner of the universe in 1 million years. It will still be in our galaxy. It will still be in a relatively local region of it. But it will be vastly farther from the Sun than anything built by humans has ever gone, by a margin that is hard to even express cleanly. So the practical answer is now on the table. Roughly 540 trillion kilometers, roughly 336 trillion miles, roughly 57 light years. Those are the numbers that define the journey. But that creates a sharper question now. If Voyager can go that far, does that mean it will actually reach another star? Or does 57 light years of travel still not mean what most people think it means? 1 million years sounds like enough time to reach another star, but that is where the story breaks from what people expect. Voyager 1 is going far, very far, but that does not mean it is going to arrive anywhere in the way people usually imagine. Voyager 1 was never built to fly to another star and stop there. It was not launched as an interstellar rendezvous mission. It has no system that can brake against the motion it carries now. It does not have the fuel to slow down and enter orbit around another star. It does not have deep time steering that can keep adjusting its path for hundreds of thousands or millions of years. And there is no target star built into the mission plan. That matters because people hear that Voyager is leaving the solar system and they naturally want the next chapter to be then one day it reaches another star. But reaching a star is not the same as moving in the general direction of one. To truly arrive, a spacecraft would need to line up the path very precisely, match the target's motion to some degree, and then slow down enough to be captured, or at least make a meaningful pass. Voyager cannot do that, so its future is not an arrival. It is a fly-through, a drift, a continued crossing of interstellar space without any planned destination waiting at the end. That does not mean stars are irrelevant. It means the way stars matter is different. Over very long times, Voyager may pass relatively near some stars. That is a much more realistic way to say it. Not reach, not arrive, not visit, but pass near. And even that phrase needs care, because near in astronomy can still mean a massive distance. It can still mean trillions of kilometers, or trillions of miles. A close stellar pass in galactic terms may still look nothing like the human idea of approaching a world, seeing details, or entering a star system in any dramatic way. It may just mean Voyager moves through the outer region of a star's wider neighbourhood and keeps going. That is one of the biggest corrections this section needs to make. People tend to think in straight narrative lines. First, a spacecraft leaves Earth, then it leaves the planets, then it leaves the solar system, then it reaches another star. That sounds neat. It sounds like the next logical step. But real space is not organised around human storytelling. The space between stars is mostly empty. That is the core problem. Stars are not packed together in any way that makes casual encounters common. They are separated by huge distances. So even though Voyager is moving through the galaxy, that does not mean it will soon pass close to some star in a dramatic sense. The odds of a very close encounter on short cosmic timescales are low. This is where people often underestimate just how empty stellar neighbourhoods are. Our sun is not sitting in a crowded cluster where stars are all close together. It is in a region where the nearest stars are still several light years away. That is a sparse environment, so a spacecraft can travel a long time, even by deep time standards, and still not come especially close to another star. That also means the path matters much more than wishful thinking. Voyager is not like a package with an address on it. It is not going to the next star. It is a machine on a trajectory set decades ago, shaped first by launch energy and planetary flybys, and then carried forward mainly by inertia, gravity, and galactic motion. That is less cinematic than the popular version, but it is much more interesting because it turns the question from fantasy into real physics. Its million-year future is fascinating exactly because it is not a guided story. No one is controlling the route in any active way now. No one is going to wake Voyager up in 300,000 years and point it toward a better target. The path it has is the path it has, modified only by the long, slow influence of gravity and the changing environment around it. And that brings up the most important correction of all. The better question is not, which star is Voyager heading to? The better question is which stars will be nearby when Voyager gets there. That sounds like a small change, but it completely changes the picture. The map of nearby stars is not fixed. Stars move, the sun moves, Voyager moves. A star that looks distant now may be much closer in the future. A star that is close now may be nowhere near Voyager's path later. So you cannot just open a present-day star chart, draw a line outward, and assume that is the future. Over 1 million years, the local stellar neighbourhood changes a lot. The stars around Voyager will not be arranged like the stars around us today. Constellations, as we know them, will be gone. Distances between stars will shift. Relative positions will change. So any serious attempt to predict Voyager's future stellar encounters has to treat the stars as moving targets. That is why this question is harder than it first seems. It is not enough to know Voyager's speed. It is not enough to know the rough direction. You also need to know how the surrounding stars are moving over deep time, and how gravity slightly bends or alters paths along the way. The future neighbourhood has to be modelled, not assumed, and that takes the tension even higher, because it means Voyager's story is not just about the spacecraft anymore. It is about a moving object trying to cross a moving galaxy filled with other moving objects. There is no static finish line. There is no fixed nearby star waiting for it in the way people imagine. There is only motion, changing geometry, and time. So will Voyager 1 ever reach another star? In the strict sense people usually mean, almost certainly not. It will not arrive and settle into orbit. It will not become a visitor in a star system by design. It will remain a drifter. Could it pass near stars over immense time? Yes, that is much more realistic. But even then, near may still be far beyond anything a normal person would call close. And that should push the story into the next level of scale, because even this whole question still assumes the galaxy is just a backdrop. It is not. The sun is moving fast around the Milky Way, and Voyager is riding inside that bigger motion, whether we think about it or not. Voyager 1 sounds like a lone object heading out into stillness, but the bigger truth is harsher than that. The galaxy is moving too. So if you try to picture Voyager's future as one straight line on a fixed map, the picture is already wrong. Start with the sun. The sun is not sitting still in the Milky Way. It is orbiting the centre of the galaxy at roughly 220 kilometers per second. That is about 790,000 kilometers per hour, or around 490,000 miles per hour. That is vastly faster than Voyager 1 is moving away from the sun. This changes the scale of the whole problem. Voyager's speed, relative to the sun, is about 17 kilometers per second. The sun's speed around the galaxy is about 220 kilometers per second. So Voyager's own escape from the solar system is only one part of its motion. The larger motion is the one it already shares with the solar system itself. That means Voyager is not just leaving the sun. It is leaving the sun while both of them are already flying through the Milky Way together. This is one of the most important ideas in the whole topic. Voyager did not start from rest in some fixed cosmic space. It started inside the solar system, which was already moving around the galaxy at high speed. So Voyager carries that motion with it. If you throw an object forward inside a moving vehicle, that object has its own speed, but it also keeps the motion of the vehicle. That is the basic idea here, without making it more complicated than it needs to be. Voyager has its own path away from the Sun, but it is also riding along with the Sun's much larger galactic motion. So when people ask where Voyager will be in 1 million years, they often picture the Sun as fixed, and Voyager as the only thing moving. That is not what is really happening. The Sun will be somewhere else too, a very different somewhere else. Over 1 million years, the Sun itself will move a major distance along its orbit through the Milky Way. It does not complete anything close to a full orbit in that time, because one trip around the galaxy takes hundreds of millions of years. But even a small fraction of that orbit still means a huge physical shift in position. So the question immediately splits into two versions. Where will Voyager be relative to the Sun? And where will Voyager be in the galaxy? Those are not the same answer. Relative to the Sun, you can say Voyager will likely be around 57 light-years away, as a rough estimate. That is the simpler answer. But relative to the Milky Way, both the Sun and Voyager will have moved, and their shared galactic motion becomes part of the story. Voyager is not peeling away from a stationary source. It is separating from a moving source inside a moving system. And once you accept that, the next thing gets even more unstable. The stars around us are moving too. Nearby stars are not fixed points. They are not parked in place waiting for Voyager to pass by. They have their own velocities, their own directions, and their own orbits within the galaxy. Over thousands of years, that is already enough to slowly reshape the sky. Over 1 million years, the change becomes extreme. So Voyager's future environment will not look like today's star charts. The stars that seem close now may not be close then. Stars that are far now may drift into a more relevant position later. The entire local stellar neighbourhood is dynamic. That means if someone could somehow look out from Voyager 1 in the distant future, the sky would not match the one we know. Constellations would be broken apart. Familiar patterns would be gone. The local arrangement of stars would be rearranged beyond recognition. That point matters because it destroys one more quiet assumption. People tend to think of the galaxy as background. Something huge, yes, but still basically still. In reality, the galaxy is not scenery. It is active structure. It is a gravitational system in motion. The Sun is moving inside it. Nearby stars are moving inside it. Voyager is moving inside it. And all of those motions overlap. So Voyager's future is not a straight path drawn across a frozen picture. It is a path through moving structure. The map changes while the spacecraft moves across it. That makes long-term prediction much harder, and it also makes the story much more real. This is where the tension increases again, because now even the rough answer starts to feel incomplete. Saying Voyager will be about 57 light-years from the Sun is useful, but it leaves out the bigger machine that both Voyager and the Sun are inside. And that bigger machine keeps everything in motion. That also means the future of Voyager is shaped by more than just speed. The galaxy itself can change the context of the journey. Nearby stars can shift the neighbourhood. Gravity can slowly bend paths. Over short times, you can ignore a lot of that. Over 1 million years, you cannot. So the real picture is bigger than a spacecraft leaving home. It is a spacecraft separating from its home star while both are being carried through a moving galaxy filled with other moving stars. That is why the question never stays simple for long. And once the whole Milky Way becomes part of the story, the next question gets sharper. If everything is moving, and if even weak forces have huge amounts of time to act, then what can actually change Voyager 1's course over the deep time? Voyager 1 looks like it is just coasting in a straight line forever, but that is not really true. Over 1 million years, even a tiny force can matter, and that means the future path of Voyager is never just one perfect line. Start with the Sun, because even now the Sun is not done with Voyager. The spacecraft is escaping, yes, but escape does not mean the Sun suddenly stops affecting it. Gravity does not work like a switch. It gets weaker with distance, but it does not snap to zero, so Voyager's path still carries the mark of where it came from. The shape of the trajectory still remembers the solar system. In a rough sense, Voyager is free and moving outward, but in a deeper sense, its motion is still being shaped by the Sun for a very long time. the path becomes more and more like a final outgoing track. But that change is gradual, not instant. That matters because people often picture escape as a clean break. First bound, then unbound, and after that, totally separate. Real motion is more subtle. Voyager leaves with momentum, but the sun still curves and defines that motion over long distances. So even when the spacecraft is deep into interstellar space, the story of its path still starts with the solar system and still carries that memory forward. But if the sun is not the only force, then what else can interfere? This is where things get less certain. Passing stars are one of the biggest long-term complications. A star does not need to get incredibly close to cause some change. Over everyday timescales, a distant stellar passage might seem irrelevant. Over 1 million years, it becomes a part of the calculation. The effect is usually small. That is important to say clearly. We are not talking about Voyager being violently thrown onto some new course every few thousand years. Most of the time these effects are weak. But weak is not the same as meaningless when the clock is this long. A small gravitational nudge can slowly add up. Not because the nudge keeps growing on its own, but because even a small change in direction or speed can produce a different final position when you let the motion continue for immense spans of time. That is one of the hardest parts of deep time prediction. Tiny changes early on can become real differences later. So if you ask exactly where Voyager will be in 1 million years, passing stars are one reason the answer has a range, not just one point. The spacecraft is moving through a galaxy where other stars are moving too, and some of those moving masses can slightly perturb its course. Now here is the next thing people often get wrong. Interstellar space is not dense enough to stop Voyager quickly. It is not like air. It is not like ocean water. Voyager is not ploughing through a thick substance that will slow it down hard and fast. The interstellar medium is extremely sparse. There are atoms out there. Ions, dust, magnetic fields, high-energy particles. But the density is so low that Voyager will not crash into the medium in any normal sense. It will not burn up, it will not lose speed in some dramatic, cinematic way. It will not suddenly stall. That is the good news for the spacecraft's long-range survival as an object. But there is a harsher side to it too. A very thin environment can still do damage if you give it enough time. Dust grains matter. Radiation matters. High-energy particles matter. Over millions of years, Voyager's surfaces will be exposed to constant slow damage. Tiny impacts can pit metal. Sensitive surfaces can degrade. Coatings can age. Materials can weaken. The spacecraft will not be ripped apart all at once. But it will not stay unchanged either. That is an important distinction. Interstellar space will not stop Voyager quickly, but it will wear Voyager down slowly. The journey is not dramatic in the way a crash is dramatic. It is harsher than that in a quieter way. Damage accumulates. And then there is collision risk. Space is mostly empty, so the chance of Voyager hitting something large is extremely small. That part should be clear. It is very unlikely to collide with a planet, an asteroid, or some large body in any direct way. The galaxy is too empty for that to be the normal expectation. But over very long time periods, probability starts to feel different. Even unlikely things stay on the table when the timescale becomes huge. That does not mean a major collision is likely. It means it is not mathematically impossible, and deep time forces you to respect even small chances. Still, the more realistic threat is not a big impact. It is constant tiny impacts. Dust is the real long-term abrasive. Dust grains moving at high relative speed can act like microscopic projectiles. One grain does not matter much. But over immense spans of time, repeated dust impacts can slowly sandblast exposed surfaces. That means the future Voyager is not just a silent version of today's spacecraft, frozen in perfect condition. It will be older in a physical sense, more worn, more scarred, more damaged by the environment it moved through. And now the bigger problem appears. If the sun still matters, if passing stars can perturb the path, if the local environment can slowly affect the spacecraft, and if tiny uncertainties can grow over time, then can we really say exactly where Voyager will be? Not exactly. Not in the strict sense people usually mean. Over short times, space navigation can be precise. You can predict positions very accurately. You can track objects, model forces, and get clean answers. But 1 million years is not a short time. On that scale, the question changes form. It becomes less like reading a GPS coordinate and more like defining a corridor of likely outcomes. A band of possible positions, a region shaped by current motion, known physics, and growing uncertainty. You still have a best estimate. You still have a central answer. But around that answer, the uncertainty widens. That does not mean the science becomes useless. It means the science becomes honest. The farther out you go in time, the more where will it be turns into where is it most likely to be. That is how deep time prediction really works. So Voyager's future path is not random, but it is not perfectly fixed in the simple way people want either. It is shaped by the sun, modified by passing stars, carried through the galaxy, and slowly affected by the sparse but real interstellar medium. That is why the future of Voyager is both predictable in broad strokes and uncertain in fine detail. And that raises the next tension point immediately. Because even if we know roughly where it will go, and even if we know the path will slowly drift, what will Voyager 1 itself actually be like after 1 million years of cold, radiation, dust, and total silence? Voyager 1 will go very far, but the harder question is what will still be left of it when that time has passed. Because in 1 million years, the real change is not just distance. The real change is that Voyager will stop being a working spacecraft and become a dead object moving through space. The first part of that is simple. Voyager 1 will be completely silent. Its power source was never meant to last anything close to 1 million years. Long before that, its instruments will shut down, its transmitter will stop, its systems will fail one by one. And then all together. There will be no more data, no more signals, no more contact. That means in the distant future, Voyager 1 will not be a mission in any normal sense. It will not be exploring. It will not be observing. It will not be reporting anything back to Earth. It will just be there, moving, cold, dark, and inactive. That is important because people often talk about Voyager as if it will keep doing what it does now forever. It will not. The motion will continue. The functioning spacecraft will not. So what does an object like that become? It becomes a machine without power, without awareness, without activity, still carrying the shape and materials of its origin, but no longer doing any work. That is the version of Voyager that will enter deep time. Then comes the next harsh reality. Extreme cold will dominate almost everything. Far from stars, space is very cold. In the short term, sunlight and internal power sources can warm parts of a spacecraft. That matters now. It matters over mission timescales. But over deep time, once Voyager is far from the sun and its internal systems are dead, those sources of heat fade out of the story. What remains is a background environment only a few degrees above absolute zero. That does not mean every part of Voyager instantly reaches one simple temperature and stays there forever, but it does mean the overall thermal world around it becomes brutally cold. There is no atmosphere to hold heat, no warm environment, no active system inside it trying to maintain stability. So Voyager will spend almost all of that immense future as an object preserved in cosmic cold. And that sounds like protection, but it is only part of the truth. Cold slows some kinds of decay. It can help preserve structure. But space is not a perfect storage box. It is not a museum case. It is cold, yes, but it is also full of radiation. Cosmic rays and other high-energy particles will keep hitting Voyager for the entire journey, not in one dramatic burst, but slowly, continuously, without stopping. Over long enough periods, that matters a lot. Electronics, polymers, coatings, wires, insulation, surface layers, all of them can be damaged by radiation. This is a kind of aging that does not look familiar to us because it does not happen like weather on Earth. There is no rain, no wind, no oxygen-driven rust in the usual sense, no biology. But that does not mean there is no damage. It just means the damage comes from different sources. Radiation can break chemical bonds. It can weaken materials. It can change surfaces. It can slowly degrade things that were once precise and engineered. So Voyager will age without weather, but it will not age without change. That is one of the strangest things about space. It can preserve and destroy at the same time. It preserves because there is no thick atmosphere, no ocean, no active geology tearing the spacecraft apart. But it destroys because radiation never really stops, and over immense time, even small damage becomes serious damage. Then there is dust, and dust may be even easier to underestimate. Interstellar space is sparse, but it is not empty. Tiny particles are out there. And when a spacecraft moving through space encounters even a very small grain at high relative speed, that grain carries real energy. Not enough to shatter Voyager all at once, usually, but enough to do damage on impact. So over 1 million years, Voyager will not just be sitting in clean vacuum. It will be taking hit after hit from microscopic particles. Tiny impacts can pit metal. They can scar exposed surfaces. They can roughen edges. They can damage delicate features over time. The big dish antenna, the booms, the outer layers, them can slowly take that wear. This is not the kind of damage that makes for one dramatic event. It is more like endless abrasion. Very slow, very small in each moment, but relentless. Over geological spans of time, that matters. And this is where the physical future of Voyager becomes more severe. You should not picture the spacecraft after 1 million years as a perfectly preserved museum object floating untouched through space. It is more accurate to picture a silent machine that is still recognizable in broad form, but increasingly worn, pitted, damaged, and altered by radiation and dust. Now bring that down to the most famous part of Voyager, the golden record. The record is one of the reasons this spacecraft carries such emotional weight. It is not just hardware, it is also a message, a physical record of sounds, images, and information from Earth, meant as a sign that intelligent life built this object. That is why people naturally want to know if it could survive for huge spans of time. The answer is maybe for a very long time, but not forever unchanged. That is the key point. The golden record may outlast nations, languages, maybe even civilization as we know it. It may survive longer than most other traces of the age that created it. But it does not outrun physics. Radiation still acts on it. Dust still acts on it. Time still acts on it. So the record is both an artifact and a durability test. It is a human message, but it is but it is also a material object exposed to a brutal environment for immense lengths of time. It may remain physically present for a very long time. Whether it remains readable in the original, intended sense after such an extreme span is a different question, and that makes Voyager's physical future more powerful, not less, because the spacecraft is not immortal. It is durable, but not permanent. It is built to last in a harsh environment, but not to escape damage forever. In 1 million years, it will likely still exist in some form, but it will be changed by that journey. So this is the real image of Voyager 1 after 1 million years. Silent, powerless, deeply cold, slowly damaged by radiation, slowly worn by microscopic impacts, still moving but no longer alive as a machine, still carrying the traces of its makers, but no longer able to speak for itself. And that creates the next question immediately, because if Voyager becomes a dead artifact in interstellar space, then what would it actually mean if someone, or something, ever found it? Voyager 1 is carrying a message, but the brutal truth is that almost nobody is likely to ever see it. That is what makes it so strange. The spacecraft was built as a machine, but it also carries clear signs that it came from intelligence. Even if no one could read a word on it, Voyager would still look artificial. Its shape is engineered, its dish antenna, its instruments, its structure, its materials, none of that looks like a rock, a comet, or a random fragment. And then there is the golden record, with symbolic instructions attached to it. So the spacecraft is a message even before anyone understands the message. The object itself says that it was made. That matters, because when people talk about contact with another civilization, they usually jump straight to language. Could they decode it? Could they understand the sounds? Could they make sense of the images? But before any of that, they would first have to recognize that Voyager is not natural. And that part is actually the easiest part. It is very obviously engineered. So in that sense, Voyager already succeeds as a statement. It says that somewhere, at some point, technology existed and someone built this. It is evidence of intelligence in physical form. But then the harder part comes in. Detection is far more difficult than science fiction makes it seem. Voyager is small. It is dark. It is silent. It is not broadcasting forever. It does not glow in some special way that makes it easy to spot. It is moving through a region of space that is almost unimaginably empty. So even if another civilization existed somewhere in the galaxy, the odds of them casually finding Voyager are extremely low. That is one of the biggest reality checks in the whole story. Space is not crowded. It is not a place where ships are constantly crossing paths. A single spacecraft in interstellar space is incredibly hard to find. Once Voyager goes dark, it becomes even harder. No signal, no active beacon, just a small cold object moving through darkness. So if someone found Voyager 1, that would not be a casual event. It would be extraordinary, not just because of what Voyager is, but because of how hard it would be to detect something like that at all. And that leads straight to the truth about the golden record. It was not attached to Voyager because discovery was likely. It was attached because the possibility mattered. That distinction is important. The record was aimed at possibility, not probability. The people who designed it understood that the odds were tiny. They were not pretending this was a realistic mail delivery system to another civilization. They knew the galaxy is too empty, the spacecraft is too small, and time is too vast for that to be a likely outcome. So why do it anyway? Because sending a trace of humanity outward had meaning on its own. The record is science, yes, but it is also something more direct than that. It is a decision to leave behind evidence that we were here, that we could build, think, encode, and reach outward. It is practical in construction, but symbolic in purpose. And that makes Voyager different from a lot of other spacecraft. Most machines are built to do a job and then end. Voyager was built to do a job, and it did that job brilliantly. But it was also given a second role, to become a long-term artifact, a message carrier. Not because success was expected, but because the gesture itself mattered. Now take that one step further. Another civilization may never find Voyager, but future humans or descendants of humans might care even more. 1,000,000 years from now, if humanity still exists in some form, Voyager 1 could be one of the oldest surviving technological objects from the early space age. That would make it far more than a spacecraft. It would be a time capsule, a relic from a period when humans were still near the beginning of spaceflight. Think about what that means without making it grander than it needs to be. To future humans, Voyager might not just be interesting because it went far. It might be important because it survived, because it carries early human engineering, early human assumptions, early human design choices, and a very early attempt to say, this is who we were. That could make Voyager more valuable to us than to anyone else, not as a vehicle, not as a scientific platform, as a surviving object from one of the first eras of outward expansion. And that is where the story changes one last time. Once a mission ends, a machine does not stay just a machine. It enters story. Voyager 1 has already started to do that. Even now, people do not talk about it only as hardware. They talk about it as a symbol, as proof of reach, as a marker of what humans were able to do with limited technology and a lot of ambition. In 1,000,000 years, that effect only gets stronger. The physical spacecraft may be tiny against the galaxy. It may be damaged, silent, and almost impossible to find. But the idea of Voyager may become even bigger than the object itself, because once engineering survives long enough, it starts to feel like mythology. Not fantasy, not fiction, but something built in one age that carries meaning far beyond the age that made it. That is why finding Voyager would matter so much. Not because it would trigger some automatic first contact scene. Not because the golden record was a likely handshake across the stars. It would matter because it would prove that one civilization, on one planet, once built something meant to outlast its own moment. And now the pressure closes in on the final question. After all the speed, all the distance, all the motion, all the uncertainty, and all the physical decay, where does that leave the actual answer? In plain terms, where will Voyager 1 be in 1,000,000 years? So after all of that, what is the actual answer? In 1,000,000 years, Voyager 1 will most likely be about 57 light-years from the Sun. That is the practical answer. In metric terms, that is about 540 trillion kilometers. In imperial terms, about 336 trillion miles. That is the number that matters most. It is not perfect down to one exact point, because over that much time, small gravitational effects, passing stars and changing reference frames all introduce some uncertainty. But as a solid first answer, about 57 light-years from the Sun is the right scale. And that distance is enormous. It is far beyond anything humans have ever sent. It is far beyond the planets, far beyond the heliosphere, far beyond the part of space that feels local to us. By human standards, it is almost impossible to fully take in. But even then, Voyager 1 will still be deep inside the Milky Way. That is the part that keeps this whole story under pressure. Because 57 light-years sounds huge, and it is, but the Milky Way is about 100,000 light-years across, so Voyager will not have crossed any major fraction of the galaxy. It will still be inside our galaxy, still inside the broad local galactic environment, still just a tiny moving point inside a structure that is vastly larger than the journey it has made. So the final answer is not that Voyager escapes into some distant other realm. It does not leave the galaxy. It does not come close to crossing it. It stays inside it, just much farther from the Sun than anything humanity has ever built. And there is one more layer to make that answer more accurate. In 1 million years, Voyager will not just be a certain distance from the Sun. It will also be in a different stellar neighbourhood than the one we know now. That matters because the stars around it will not match today's sky. The Sun will have moved, nearby stars will have moved. The local arrangement of stars will have changed. So the best way to describe Voyager's future is not only with distance, but with context. It will be moving through a future version of the local galaxy. The stars around it may be unfamiliar compared with the stars we know today. The sky, from Voyager's position, would not look like our sky. The local map will have shifted. That makes the answer feel more real. Voyager is not just going farther into the same frozen scene. It is moving into a changing environment, into a different nearby galaxy than the one we see now. Not different in the sense of a different galaxy entirely, but different in arrangement, in local traffic, in which stars are near and which are not. And by that time, Voyager 1 will no longer be a mission. That part is final. It will be dead as a spacecraft. No power, no instruments, no signal, no active science. It will not be exploring in the way people usually mean. It will be a cold, silent object in motion. But that does not make it meaningless. In some ways, it makes it more important. Because at that point, Voyager 1 becomes a monument. Not a monument fixed in one place, but a monument still moving. A machine built by a young technological civilization, still coasting on momentum long after the world that built it has changed beyond recognition, or vanished entirely. That is the real force of this question. You start by asking for a location, and you end up with something bigger than location. Yes, the practical answer matters. About 57 light-years from the Sun, about 540 trillion kilometers, about 336 trillion miles, still inside the Milky Way, likely moving through a different local stellar neighbourhood. But the bigger answer is about time. Voyager 1 will be carrying proof that, for a brief moment, a species on Earth learned enough to build a machine that could outlast its own age. Long after the mission ends, long after the signal stops, long after everyone alive today is gone, that object will keep moving. Far from the Sun, still inside the galaxy, silent, cold, and damaged by time, but still there. And that is the final answer. Voyager 1 in 1 million years will not just be somewhere else. It will be evidence that humans were here, that they reached outward, and that one of the things they made kept going long after their moment had passed. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.